Hello, my name is Dan Wolf. I'm a Senior Director of Development at MSC.Software, and today I'm going to talk about how we perform finite element analysis to predict, examine, and validate events experienced with plastic gears. This work is from a paper presented at the annual meeting of the Society of Plastic Engineers by Ticona and MSC.Software. The simulation is performed with the Mark Finite Element program from MSC.Software. The Spur gears, geometry, material data, and test machines were provided by Ticona. The primary function of these Spur gears is to transmit rotational motion from one gear to another. The design of the kinematics of the gear set is geometrically controlled as if it were a rigid body. However, for real materials, the choice of materials becomes critical in the design. The geometry of the gear teeth was based upon standards from the American Gear Manufacturers Association. A parallel axis gear testing machine developed by Ticona, shown here, was used to load and record the load displacement response of the gears. The test gears were lubricated with oil prior to loading. A schematic of the test chamber is shown here. Torque was measured on the stationary side and load was applied on the motor side. Two high-precision encoders were used to measure the angular displacement of both gears. These encoders have a positional accuracy of about 60,000 counts per revolution, and the rate of loading was about 2,000 radians per minute. The outer plane thickness of the gear rim is about 1/4 of an inch. The stress-strain data is shown here, where the maximum strength of the material is approximately 8.5 KSI. 5 tests were made per gear at ambient conditions, and a plot of the applied torque versus the twist is shown here for all 5 tests that were very repeatable. One of those was used to compare with the results. The full gear is modeled instead of a sector to capture the correct torsional stiffness of the gear. One method of failure is to separate the teeth at the root using a contact option where the tensile strength exceeds 8.5 KSI, and another method is to simply deactivate the elements as soon as the tensile strength exceeds the 8.5 limit. Here we see the gears in action. Here we see the teeth separating at the root, and we'll see it again where the teeth are, the material is deactivated, the elements are deactivated. And here we see the comparison of the experimental and analytical results. The yellow curve is the experimental. All the other curves are the predictions that overshoot and undershoot depending on the various assumptions. In conclusion, the prediction of the gear pair is very complex. The rigid design does not account for the gear flexibility. To optimize the gear set, a nonlinear analysis is required, and only under very low loads can a linear analysis be suitable. Thank you for watching, and if you'd like to learn more about MSC.Software, as well as other tools to help you simulate, you can visit us at www.mscsoftware.com.